This lab does not have a major analysis section. Your students may ask why the hopper jumps to a different height each time. This could be due to how they fold the hopper over on itself, or some variability in the internal structure of the rubber. Let's face it, these are not expensive pieces of lab equipment. These would be systematic errors as opposed to human error in reading the meter stick precisely. As mentioned earlier, sometimes students with cameras in their phones like to take a clip of the hopper going up, then look at it frame by frame to find the maximum height. This takes longer, and frankly not always acceptable. That's pretty cool. Analysis and application questions. These would be good to give to your students. First one, what is the velocity of the large hopper at the instant before it hits the table? Try not to ask them what's the velocity when it hits the table, because a lot of kids will just say, hey, it's 0, it's stopped. You want the velocity right before it hits the table. And prove your answer using one of the given kinematics equations. So the process is first calculate V0 using the first kinematics equation. And what's your velocity at the top here, where your time is half of t max? Well, the velocity will be 0. So V0 will equal minus a times t max over 2. You just rearrange the first kinematics equation. And we're trying to find this V0 right here. We'll now reuse the first kinematics equation, but we want to find the velocity down here, which is what we asked originally. So this time, what's the difference? The time will be t max. So in the previous slide, we solved for V0, and we'll insert it into the equation there, and we get V is equal to minus a times t max over 2 plus a t max. Well, you combine those two, and you get velocity, your final velocity right before it hits the ground, is a times t max over 2. Then note, here's V0, minus a times t max over 2. Here's your final velocity. So your final velocity is negative your initial velocity. You compare these two right here. Let's switch to a graphical analysis. When you plot a line, you only need 2 points. We know that at time equals 0, the velocity is V0. That's this point right here. We also know that the velocity is 0 at time 1/2 t max. So we go ahead and plot this point. Then we connect them up, and we have a velocity time graph for the hopper lab. Since this is a velocity time graph, when we take the slope of the line, and the slope is rise over run, right, or delta y over delta x, we have v over t, which is the acceleration. And in this case, since the hopper is in free fall once it's launched, the only acceleration is due to gravity. That's the definition of free fall. The acceleration and the slope of the graph should be negative 9.8 meters per second squared. Using the results that we've obtained from the small and large hoppers, plot the velocity time graph. Plot the results for both hoppers on the same axes. So we have a velocity time graph below, and our results for the large hopper, this was our initial velocity. This is how long it took to get to the apex position. We actually don't need the x values here, but we put them for completeness. This is the result from plotting the 2 points we obtained on the previous slide. So let's look at the large hopper, which is the top line here. At time 0, this was the initial velocity that we calculated. And then at the apex time, which is where velocity was 0, so you're going to be on the time axis here, you have this point. Okay, that's 0.36 seconds was your apex time where your velocity was 0. You connect the two lines up. You do the same thing for the small hopper. And these two lines have the same slope. It's easy to see because lines with the same slope are parallel. The results should make sense because they're both subject to the acceleration due to gravity, which is negative 9.8 meters per second squared. The negative slope, that's what gives us the negative sign, and the acceleration is downward or in the negative direction. Calculating time of flight and initial velocity of the hopper from its height relies on the fact that the acceleration due to gravity is constant, and of course that's negative 9.8 meters per second squared. Knowing either the time of flight or the maximum height, we can calculate the other. Much of the error in this lab is due to the folding over of the hopper affecting how high it will go. Additionally, there will be errors in reading the meter stick as well. We do multiple trials to reduce that error. Recording the hopper with the slow motion camera on your phone can further reduce this error. Although air resistance is minimal, it still reduces the maximum height of the hopper. However, this error would be small compared to the other two.